Welcome to lecture 22. In this lecture, we'll talk about real-time POSIX. So what we have seen in Windows and Linux that we have the notion of a thread time slice, which is of course much larger than the timer interrupt interval. So in the Windows, it can be large. So of course, these are configurable parameters, can vary between 10 milliseconds and 120 milliseconds. The kernel as such is preemptible to a large extent, which means it's also reentrant. So in Windows, of course, background processes, the time quantum is slightly smaller, foreground is slightly larger. So there is a 1 is to 3 priority difference between background and foreground. So again, these are processes of the same base priority. In Linux, the thread quantum again varies between 10 to 200 milliseconds, defaulting at 100 milliseconds. Again, this varies quite a bit based on the nature of the task, the parameters that the user has supplied, right, and also how much CPU time it has used, and so on. Again, the key features are reentrancy and preemptibility to different extents. So the scheduling priorities are slightly interesting in Windows and Linux. So Windows, as you have seen, is from 0 to 31, but most of the time the idle process has priority 1. And most processes actually have their priorities in this range, the dynamic range, right? So these are for very low, priority background tasks. And this is the real time range. Higher the number, higher the priority. In Linux, on the other hand, things are slightly more complicated. So what happens is that we have 140 priority levels, right? And so at this point, so the real time priorities are pretty much from 0 to 99. So in this case, higher is the number, higher is the priority, right? So at least, this is the case for many versions of Linux that I have seen. Fair for, for this zone, higher is the number, higher is the priority, in the sense the priority of 99 would make it the highest priority process. Then the normal range would be at 120. So you can, of course, add a nice value and you can kind of go up, right? So which means you can decrease your priority, because after 100, higher the number, lower is the priority. So pretty much what happens is that the priority increases this way as we approach 99. So of course, if this is the priority, if I add a nice value which is negative, then of course I'll be going up towards 100, in a sense increasing my priority, which in ideal cases is not allowed. So this would require super user permissions or kernel permissions. But I can always be nice to another process and reduce my priority. So in that case, I'll have a positive nice value. That's the reason most CPU intensive tasks would sort of be over here. And most IO intensive tasks or other, very low priority kernel threads would be over here. So as you can see, unlike Windows, Linux does not have any explicit mechanism, or, not, I wouldn't say explicit mechanism, but, any kind of a special feature for actually running interactive tasks with a high priority. But that said and done, it is far more expressive in terms of real time priorities, because even many kernel routines and many kernel threads actually use real time priorities. So, again, the way the scheduling is done is quite simple. We consider all the priorities at the same, all the processes at the same level. So, let us say that this is priority 25. We have a choice for all the processes that are in priority 25. Either we use FIFO or we use round robin, right? So this choice is something that we have. But definitely, at least in the real time world, if I have a process with a higher priority, in the sense which is more real time, I will always run that. So as we have seen on Windows, there are two scheduling classes: a real time fixed priority between 16 and 31, and a class from 1 to 15 where the priorities can vary depending upon the behavior of the process. And naturally, higher priorities are favored. And also, the priorities of dynamic threads get boosted when they wake up. In the sense, what I mean by that is that, let's say they are sleeping, or they're waiting for an IO to complete. So the moment the IO comes and the thread becomes a foreground process, its priority is boosted, right? So in general, thread priorities are never lowered unless, of course, the thread is trying to be nice. Now let us come to Linux. So Linux, as we have seen, has three priority regimes. So you have the normal mode between 100 and 139, and then we have the real-time mode between 0 and 99. Right, so they of course operate differently as we have discussed. So the real-time processes, we have a choice of schedulers. One is fixed round robin and the other is fixed FIFO. So in very old versions of Linux, the complexity of scheduling used to be order n, because if there are 10 tasks, there was a need to scan all of them and find the one with the highest priority. But after 2.6, things are better in the sense we have per CPU queues, so you don't have to check the queues of other CPUs. And again, this is more like a radix tree where tasks are sorted by their priority, right? So basically, this structure is known as a radix tree where the tasks are sorted by their priority. So you go to a priority level, you'll find all the tasks organized as a linked list. So this is where both FIFO and round robin scheduling can be used quite easily. So coming to POSIX, this was a very popular standard, still is. It's a basically a portable operating system interface which was meant to create standard policies, APIs, and interfaces across operating systems and also increase the availability of add on packages. In the sense, it should not be necessary for a developer to write different pieces of code for different operating systems. The same code should ideally run on all with hardly any modifications. And also, make the process of coding for a diverse set of operating systems quite easy. So this will facilitate system integration and porting. So genesis of POSIX, so Unix was made freeware by AT&T, right, in the 80s. Many vendors extended Unix in different ways. So many of these were also commercial operating systems. So IBM Unix was known as AIX, HP was HPUX. Sun's Unix particularly became very popular and very famous also because in the dawn of the internet era, Sun used to provide most of the network switches and networking hardware. So essentially, the internet was built on top of it. So Solaris was the operating system, and also a very influential company towards the late 90s was the Digital Equipment Corporation, DEC. So DEC's Unix was Ultrix, right? And then of course we had SCO Unix and so on. So if you can see, this is like a family tree of Unix. So of course there was a VAX VMX system. So this tree completely died because the VAX machines themselves died. But Unix, as we know, has been there since last 60s. So one very important tree which is still used in a lot of commercial settings is the BSD version, Berkeley Standard, distribution. Then, as I said, Solaris became very important because of the internet and because of the features that it provided. And then, of course, we had System 3, 5, and so on, and the IBM and HP versions. But because they were proprietary, they didn't become that popular. But what actually became very popular was the versions of Linux, which in a sense drew from the Unix philosophy, even though the kernel was separately developed. But it is still quite compatible with existing Unix systems. Now, coming to POSIX. So programs on one version of Unix should ideally run on another. Different Unix versions will offer different services. The syntax and service semantics used to differ. So, excuse me, I'll show this once again. Right, and so the standard version had issues. So the first effort towards Unix standardization was made by AT&T with the System 5 interface. It is just that at that point, the Unix community there was a fork. So System 5 and AT&T went in a separate direction, and the developers of the Berkeley Unix went in a separate direction. But then IEEE took an initiative in 1990, and this yielded the first POSIX standard IEEE 1003. So then at that point of time, towards the mid to late 90s, open source software came in a big way, where the source code is distributed. So Unix as such is an open software. Many versions of it today, if you look at it. Even Solaris later on got open sourced. So the open source software, if you see Wikipedia, this basically means that it permits users to study the software, change it, improve it, and also redistribute the software. Here again, there are different licenses, and those licenses vary. Some licenses tell you that, look, take the software, do anything you want to do with it. But other licenses, such as the GNU public license, which comes with Linux, well, does not allow you to do that. So any product that you create and distribute also it needs to include the source. So open systems versus open software, they are not the same. An open system is a much broader concept, right, which includes the software as well as the protocols, the networking, even parts of the hardware. So open system is really open, right? It has open interfaces and standards and so on. Open software is an offshoot of this concept. So an open system, ideally speaking, is vendor neutral. In the sense, because all the interfaces are standardized, it allows you to create a custom mix of hardware, of software and networking solutions. Choose whatever that suits you best from different vendors, and also take in third party solutions, right? If they suit you. And because we have standardized interfaces, it is guaranteed that these systems will work. They'll mutually work, right? So the entire system is going to work. So the open system has been there with computers and software, which has really led to the growth of the industry. So it is now possible to replace, let's say, my keyboard or my mouse with a keyboard and mouse of a different company. Things still work. On my hardware, I can install a different operating system. Things still work. That is because we have standards, and these standards ensure that regardless of the hardware and software, there is a degree of compatibility, right? So, although interoperability is a standard concept now, in the sense that if I buy a device, I expect it will work on my hardware, it will work on my software. But in the late 70s, this was not the case. The Unix vendors were promoting the open system concept, but it had still not come up, right? So, we still had a lot of proprietary hardware and software where the software did not run on each other's systems, right? So, this was resisted by a lot of major vendors. So open systems and standards are not copyrighted. So which means that you can use Linux and Unix in your work, and it saves users and vendors from very expensive lawsuits. That is one. There is a degree of interoperability and portability, which is very important in a modern world where you have so many hardware and software vendors. So from that open system movement, the POSIX standards, they were an offshoot. So what is a major concern of POSIX? It is that at the source code level, right, at the level at which we write our code, let's say in C or C++, the application should be portable, which means I write code, let's say on Linux, the same code should run on Windows. If you see nowadays, that is more or less the case. So consider, let's say, the VI editor. Whatever is written on Windows, you can take the same code, run it on Linux, it'll work. By and large, it's going to work, right? So across Unixes and Linuxes, it will work. Windows is a separate situation. We will discuss that. But again, Windows does provide a lot of POSIX compliant APIs. So that is why even if we are migrating the code, the amount of changes we need to do is not much. So POSIX now is widely accepted. Many non Unix OSs are making themselves POSIX compliant. And POSIX, as I said, is an IEEE standard. Now it's an ISO 9945 standard as well. So POSIX defines primarily interfaces to operating system services, right? So different operating systems would have different formats for system calls, different formats for accessing data. So the interfaces have been standardized in POSIX. The semantics have been standardized. But how do you implement the specific service? That is something that POSIX has not specified, right? So this is not something which is explicitly specified as to how the service is to be implemented. So coming to POSIX, so POSIX has actually, four standards. So we are interested in the fourth in this course, but it's important to understand what the others are. So the first was the system interface. So this is at the code level, uh, to ensure that our libraries works and system programs work. This indeed is the case, because if you see the GNU libc library, glibc, which provides all the key libraries to the C and C++ code, and including others like Java, etc., who are also reliant on some part of libc at least. The key issue is that this got standardized. Shells and utilities definitely got standardized, because things like ls, grep, and so on, they work. And they work on Windows PowerShell as well, right? So a lot of these things have come into Windows as well. Then the third aspect was of POSIX was methods for testing whether a program or an interface is conforming with POSIX. So this was done. And the aim of this was to primarily test these two, that whether the system interface and the shell and utilities, whether they are conforming to POSIX or not. So what we are more interested is in the real-time extensions of POSIX, which was later on added as POSIX matured, to ensure that real-time operating systems are able to run in a mutually compatible fashion, which basically means that if some piece of code is meant to run on one system without missing deadlines, we can run it on another system and again specify the rules for executing the program. Hopefully, it will run correctly. So, many small embedded systems do operate under a lot of constraints. So, they will not support all of POSIX, but a few of POSIX's functionalities. So, that is why the real time working group identified four application environment profiles. So, application environment profiles are also called AEPs in real time terminology, for when and how we should implement which subset of POSIX. So the relevant POSIX document, as I said, is POSIX 4, which defines the interfaces to support the portability of real-time applications. So some substandards would be POSIX 4a, which are extensions for threads, and POSIX 13, which talks about the different application environment profiles. For each AEP, specific services that need to be supported by the host operating system and the host system as such are listed. So coming to AEPs, the minimum system. So we will look at some AEPs. So one is of course a highly minimal system. So this is a small embedded system with no memory management unit, disk or IO terminal. So in a sense, there is no virtual memory or any kind of secondary storage. So this would be like a very small sensor kind of system. So it will be a sensor unit. So this would fall over here. Next is a real-time controller. It is just that it has additional support for persistent storage. So it has additional support for a file system and an IO terminal, right? So basically, via which we can access the file system. Then we have, uh, you know, we it still supports a single processor. This is a limitation that a real-time controller will still simulate a single process. But of course, the way that you would simulate multiple processes via a single process is that you will basically call multiple functions. So here, this aspect also has been discussed, that how do we support that many processes? And of course, we don't support that many processes, but we simulate something to ensure that it is calling one function, and this function can, think of it as a process. It returns, then we call the next, and so on. So of course, this was our simplistic model, which we were using for EDF and RMS. But for a real-time controller, we go one step forward. So it'll still be the same one process, right? Not as simple as this, slightly more complicated, where multiple threads will be allowed. So AEPs uh, again come in two more types. One is a dedicated system, which is a large embedded system with a lot of sensors and memory model, hardware modules, I/O modules, and so on, but no support for files. And a multi-purpose system, which is basically everything, which is like a regular desktop or a server, in which all POSIX 4 features are supported. So multiple AEPs as such were defined because all of POSIX 4 cannot be supported by every embedded system. So coming to real-time POSIX, so if you look at a support for preemptive priority-based scheduling, then you need some performance metrics, right? So for every system call, you need a worst case execution time, which is also known as a worst case execution time like this. It's a bound. And so this allows us to properly plan our execution, think about worst case execution times, plan, right? Real time system is all about planning. So the moment we have an upper bound, this really helps. And this is exactly what the POSIX standard mandates for the system calls. Then we need support for static real time priorities, priorities that don't change. So recall that Windows provides some static priorities, Linux also provides in its real time range. So this is needed to for our algorithms like RMS, and we need at least 32 priority levels. So 32 static priority levels is what we need. So I'm not saying 32 and static. Well, is the standard says 32 and support for static. Not saying that how many of these have to be static, but this is essentially an extrapolation that I have made. Then we need absolute and relative timers. So we need relative timers from the previous event. And also we need absolute timers to implement clock. So this is again a requirement. Along with high precision timers, which are nanosleep functions, which can provide high precision timing where a process can just go inactive for a few nanoseconds, which is basically to do more like synchronous IO, where we don't want to go to the operating system and we want to basically sleep for some time or not do anything for some time and again do. So this is only possible either by inserting a dummy for loop, which again eats up power, or using a nano sleep function using a high resolution timer. Then virtual memory functions. So POSIX does say some very interesting things about virtual memory. So it wants systems to, at least the full standard, to implement mlock, which is to lock a page in memory. So this again gives it a deterministic access time. Mlock all is to lock the entire address space. Then munlock is to unlock a page, right? So this is there. So locking is required, which will ensure that you don't have to go to the swap space, right? Unless you want to. Multi-threading support is required. So we saw that even in the very basic version. And the issue of files is slightly tricky. So as you have seen, the way that we were defining our AEPs, many of our AEPs didn't actually have file systems because having a file system means basically from the CPU going to some sort of a secondary storage, either flash or the hard disk, right? Files by definition are stored in secondary storage. And secondary storage devices don't have a deterministic access time, right? So that is the key issue. So in terms of scheduling policies, there are three scheduling policies. So one is shared FIFO. FIFO should be supported. Round robin should be supported, and shared other is basically any custom scheduling that I would like to implement, such as EDF, RMS. So coming to this, basically shared FIFO will be a preemptive priority based scheduling algorithm, right? So this will definitely be there where you have first come first serve, and this will be a very simple scheduling algorithm which does not require any time slicing, right? So the available priority range can be identified with priority min and priority max, as you can see, for shared FIFO on Linux. So Linux supports these POSIX calls of shared get priority minimum and maximum. So for the real-time calls, as we have seen, 1 is the lowest and 99 is the highest. So whenever a shared FIFO process becomes runnable, it will always preempt a shared other process. By definition, it cannot preempt another shared FIFO process. And furthermore, when it runs, if it is blocked by an IO request or it gets preempted for some reason, it will call shared yield, right? So basically, the idea here is that either it will call or the kernel will call on its behalf. But the key point is that let's assume that there are two processes. Where process one comes first, it was running, but it had to do some IO, so it went into the kernel. And then process two is running, and then process one again comes up. So clearly, process one has the higher priorities. At this point, it is going to uh, start running again. So this is a case where the FIFO process P2 is getting preempted by a higher priority process. So if we just look at this sentence again, a shared FIFO process, while it is running, it will continue to run unless it does an IO request and it gets blocked because it's taking time for the IO to be serviced. Or as you can see in this case, P2 is getting preempted by a higher priority process. Or it decides to suspend itself, right, by calling shared yield, or it finishes. So the moment it decides to suspend itself, calling shared yield, it basically goes to the end of the FIFO queue. So it basically becomes the most recently arrived process. Shared RR on the other hand is preemptive and priority based with a time quantum, right? So it is an enhancement over shared FIFO where every process is allowed to run until its time quantum is over, which as we have seen in the case of Windows and Linux is between 10 and 200 milliseconds. And after that, the next process in its priority level gets a chance. So until all of them have finished, no process gets a chance to run once again. So again, the available priority range for real-time processes remains the same. And this POSIX call can be used to figure out what is the interval, right? The time slice by a shared RR get interval. Shared other is the default Linux time sharing scheduler, which runs at static priority 0. So as I've said, until 99, higher the number, higher the priority, right? So if you look at it, in a sense, the default Linux scheduler, which schedules all the user mode processes, this has a lower priority than every other real-time process. So every other real-time process has a priority between 1 and 99, but the default Linux scheduler has a priority which is lower than all of them. So this is clearly intended for all processors that do not require real-time scheduling, right? And basically what happens is that the role of this time sharing scheduler is to basically find non-real-time processes and to run them. So anytime the processor is not fully utilizing its slice, in the sense there is some idle time left, this scheduler is called, which is the regular Linux scheduler, right? And so then so this is primarily because the CPU is free, so no other task can be run, right? Because there are no tasks. So at that point of time, we run regular non-real-time tasks. So this is something we have seen earlier also in the case of EDF and RMS. So in traditional operating systems in POSIX 1, what happens is if a signal is sent to a process, the signals are not queued. So some signals can get lost and they are also not prioritized. Furthermore, different events of the same kind can produce signals with the same number. So we pretty much, signals were not a big deal. So that's the reason, a lot of thought was not put into them. Because let's say if a process for some reason, you can't suspend it, then you can always send a message once again. But in POSIX 4 real-time signals are never lost. They are always queued, they are never lost. We treat them very seriously. The queued signals furthermore have a priority. They are handled in priority order and they contain a few additional fields. And these fields are sometimes used to exchange data between the kernel and a real-time process or between real-time processes themselves. Furthermore, coming to the thread extensions part, we have said that the basic POSIX 1 process model is not suitable for many real-time applications, mainly because processes have very high context switch times. And also, many embedded applications do not have virtual memory. As a result, they cannot afford separate address spaces, right? How do you have separate address spaces without virtual memory? So, of course, there are other simpler schemes like base limit and so on, which you would study in a traditional operating systems course. But there are many problems with them. So, virtual memory is the best. But many embedded processors can't afford virtual memory, it's luxury. So, coming to a thread versus a process, right? It's important to make this distinction here. So, in a single threaded process, it's basically one thread, one process, one control, where code, data, file, register, stack, everything belongs to it. But in a multi threaded process, we have multiple running threads, each with their program counter. Each of them is like a sub process. The threads between themselves share the code, they share the global data, and they share the files and also the network connections. What they don't share is clearly the program counter, the set of hardware registers, they are not shared, and the stack. So every thread has its own dedicated stack and registers. So switching between threads is much easier, it's a much more lightweight option as opposed to switching between processes. And furthermore, you don't really need virtual memory to implement a multi-threaded setting in an embedded device. Can be done even otherwise. Threads have other benefits, responsiveness in terms of the fact that code data etc is shared. That makes thread creation and switching much more efficient than creating and switching processes. If you look at Solaris, creating threads is 30 times less costly than creating processes, and context switching between threads is 5 times faster than process level context switching. So, in thread scheduling, three schedulers coexist, the global, local, and mixed schedulers, right? So, in global schedulers, you can say that look, all the threads globally contained, right? Globally contained for the CPU and resources. For local schedulers, you can say that I have multiple multi-threaded processes, right? Multiple multi-threaded processes, right? Let me maybe draw it like that, right? So these are processes, and each process has multiple threads. So in this case, what happens in local scheduling is that you allocate a set of CPUs to a process, and threads only compete with other threads that belong to the same process, right? So again, in most embedded systems, we will not have the luxury of doing this because we'll not be supporting multiple multi-threaded processes, right? Unless the system is very large. But at least from the point of view of understanding the space, it's important to have this information. And mixed schedulers are where we have two kinds of threads. Some threads have global contention, and some threads have local contention. Then, if you would recall our early discussion on EDF and RMS, so we had also discussed about aperiodic and sporadic tasks, where the difference between aperiodic and sporadic was that there is a minimum delay between task inter arrivals when you consider sporadic tasks, as opposed to aperiodic tasks where that minimum delay was not there, right? So POSIX 4b talks about a shared sporadic scheduling policy, which can be used to process the sporadic events at different desired priority levels. So go back to our discussion on scheduling sporadic tasks when we are talking about EDF and RMS, and also ensure that lower priority tasks are not affected. So this ends this lecture on POSIX uh, right here. So we will continue to discuss more of real-time operating systems in the subsequent chapters.